I love a great mystery. And I'm fascinated by the greatest unsolved mystery. Do we see reality as it is?
We also move in the world. We also have sensors that collect information about the world. Why would we, contrary to the airplane, present that information to ourselves as mirror states, as opposed to whatever way makes more sense for the game of survival, which is Donald Hoffman's well-substantiated theory. It's even a mathematical theorem derived from game theory that we would not have evolved to perceive the world as it is. We would have evolved to have a dashboard.
It's saying, given that our senses evolved, we can't trust them to tell us about reality. But if we can't trust them to tell us about reality, we don't know we evolved. Period.
It's like you have to break the theory. That's a revolution when he said that, when Karl Popper said that. It's on the contrary, the knowledge, the final knowledge of the theory, because you know its limit.
If your argument works, we do not know we evolved, period. But if we don't know we evolved, then
Hi everyone, today we're going to be exploring this valid deductive argument and its implications. So first, before we get into the argument, I want to say a word about its significance. If the target conclusion here is true and the theory is self-defeating, that doesn't mean the theory is wrong. It doesn't refute the theory. What it means is we can't know it to be true. We can't justifiably believe it to be true. And if Sean Carroll is right in his argument, in his paper, Why Boltzmann Brains Are Bad, then we need to discard theories like this or find a way to upcycle them into ones that are not self-defeating, or as he calls them, cognitively unstable. So the issue with cognitively unstable theories is that they undermine their own justification. It's like sitting on the branch of a tree and sawing off the limb behind you. And we'll see why in a bit. But this is a valid deductive argument, which means we can't simply reject the conclusion. If we want to do that, we have to reject one or more of the premises. And the same goes for premise 1 and premise 2. We can't simply reject them because they have supporting deductive arguments. So if we want to reject one of them, we'll have to first reject one of the sub-premises in their favor. So we'll go through the premises one by one, then explore the implications. So this is a sneak peek of the sub-argument for premise 1. Now, obviously there's a lot going on here, so before we dive in, we're going to cover some required context. First, we're going to cover a little bit of evolutionary game theory, and then in particular we'll examine the significance of Donald Hoffman's modeling that he and others have done using the tools of evolutionary game theory, and finally we're going to consider a little thought experiment. So first, let's consider kudzu. If you've never heard of kudzu, it is a non-native plant species that when it was introduced to, I think, North America, it spread like wildfire and drove a number of other plant species almost to extinction. It has a number of features that allowed it to be so dominant. It grows super fast. It has a deep and extensive root system, which allows it to access water and nutrients more effectively than many native plants, which gave it a competitive edge. It has a high reproductive capacity. It has a tolerance to a range of environmental conditions, and it had a lack of natural predators in its new environments. So it turns out we can actually model examples like this with the mathematical core of the theory of evolution by natural selection, which was formalized by John Maynard Smith in the 1970s. The main thing that's important to know here is that the core of evolutionary game theory is this thing called the replicator equation. And this essentially captures our intuition about what's going on with kudzu and other invasive species in a mathematically precise way. It describes how the relative frequency of alleles or strategies will change in a given population, given whatever conditions there are, over time, right? So it says it can tell you what happens in the long run, and so in the evolutionary context here, that's going to translate to species either being driven to extinction or caused not to evolve in the first place if their strategies are sufficiently weak compared to other competing strategies. When this happens, it's referred to as a strategy being strictly dominated by another strategy. Now, this doesn't always happen. Sometimes there can be strategies that are roughly on par, right? So they can exist in a stable equilibrium. But these are really the three options: stable equilibrium, strict dominance in one direction, or strict dominance in the other direction if we're just considering two different strategies. So we can use evolutionary game theory to explore how various strategies compete against each other, and it has in fact been used to explore different strategies with respect to foraging, like the hawk versus dove strategy. It's been used to explore altruistic strategies versus more selfish strategies. Turns out altruism doesn't always lose, as some people used to think. And you can even use it to explore different perceptual strategies. Now, for decades, no one bothered to ask this question in a mathematically rigorous way and see what the theory had to say, because everyone assumed we already knew the answer. We knew the answer to be truer perceptions are fitter perceptions. The gazelle that does not veridically see the tiger in the bushes is going to be less fit than the gazelle that does veridically see the tiger. So of course, truer perceptions are fitter perceptions. But recently, Donald Hoffman and others did ask this question of the theory, and the results were surprising. The bottom line was that veridical perception goes extinct. Now, there's so much to say about the details of their modeling, but for simplicity's sake, I will try to be as concise as possible and as clear as possible. So let's consider a simple example that they use. This is an organism that only needs a certain amount of water to survive. Okay, so there's a Goldilocks zone for how much water is beneficial for it. Too little water and it dies of thirst. Too much water and it drowns, say. And we're also going to stipulate that this organism has 4 different percepts that it could have. It could experience 4 different perceptions. And again, for simplicity, we're just going to use colors to represent these, but they could be anything. So the question here is, how is the organism going to use the 4 different percepts available to it to map the different territories it could come into contact with? So there's 2 relevant strategies to consider here. The first is what Hoffman calls a critical realist strategy, which means it's a strategy that tries to enable veridical perception. So we can understand what's going on here if we, for a moment, step back and consider what we think is going on with how our eyeballs process images, right? So we have photons coming into our eyeballs from the environment. They're impinging on our retinas, and first of all, the image is upside down and has to get flipped, but what our brain does is it tries to make its best guess at what the most likely 3D image, right, the 3D environment was that gave rise to that 2D image that is on our retina, right? Because there are many possible 3D images that can give rise to the same 2D image. So our brain factors in things like shading and texture, and this is how, for example, we can be subject to different illusions. But the point here is that when our brain is successful at selecting out the correct 3D interpretation, right? When we see the 3D environment as it really is, then there is structure in our perceptions that is a reflection of structure out there in the world. Okay, the term here is they're homomorphic. They're homomorphisms of each other. And the same thing is going on with this water organism. So we can see that there is a ordering relationship that exists among the four perceptions here on the top graph that reflects an ordering relationship that exists in the territories. So what does this mean? So if we take a step back and consider the graph and what it's telling us here, notice that the x-axis is labeled resource quantity, and it goes from 0 to 100. So what we're doing here is we're just normalizing all the different possible territories the organism could come into contact with, and we're ranking them from 0 to 100 according to how much water exists there. So 0 might be an arid desert, and 100 might be a deep ocean, okay? And 50 is some damp soil or something. Okay, now the point is that as we go from 0 to 100, right, we go from red to yellow to green to blue. When the organism is in a territory with a little bit of water, it sees red. When it's in a territory from 25 to 50, it sees yellow. From 50 to 75, green. From 75 to 100, blue. So if the organism were to say blue is greater than green, is greater than yellow, is greater than red, right? That would be an ordering relation among its perceptions that is also true of the territories, right? The territories that map to blue have more water than the territories that map to green, than those that map to yellow, than those that map to red. So the bottom line here is that the critical realist strategy preserves the structure of the objective physical environment in its perceptions. It reflects that structure accurately. Okay, now if we consider the second graph here, which corresponds to what Hoffman calls a strict interface strategy, we'll notice that this alternative perceptual strategy doesn't preserve that same structure of the physical environment, right? Because there's no ordering relation that the strict interface strategy might want to articulate that would be correct. The primary reason for this is you'll notice that 3 out of 4 of the colors of the perceptions have been split in half. They're split in pieces across this perceptual mapping. So for example, for the strict interface strategy, the red percept maps both extremes, both when the organism is in the arid desert and when it's in or in the presence of a deep ocean. It will have the percept red in both those cases. And when it's in the more middling territories, it will perceive blue. So blue hasn't been split up, but all the others have. And so, for example, if any ordering relation the strict interface strategy might want to posit, like red is greater than yellow, say, half the time red is greater than yellow, but half the time it's not. Half the time yellow will correspond to a territory that in fact has more water than red, which might be the arid desert. So what Hoffman points out here is that the organism that has a strict interface strategy doesn't even have the appropriate language or concepts with which it could have a hope of making true claims about this structure of its physical environment. Anything it would want to say would be wrong, at least in the context where it's trying to say something about its external objective physical environment. So I hope it makes sense why we would say then that the critical realist strategy has veridical perception, right? Its perceptions are homomorphic to the structure that's out there in the world, whereas the strict interface strategy does not have veridical perception. If it still doesn't make sense, I've linked the papers, the relevant papers in the description, and there will be future videos on this topic if you're interested. Okay, so what happens when we put these competing perceptual strategies in competition with one another? Well, as I've said, the end result is going to be that the strict interface strategy strictly dominates the critical realist strategy, and we can get an intuitive sense for why that is by considering these water organisms here. So if we imagine that there's a number of territories available to each of the organisms to choose to go to get water from, then if we can pick any numbers. You can try this yourself with a random number generator, but imagine that the critical realist strategy has a choice, right, between a yellow territory and a green territory. Well, both of those territories are equivalent in terms of fitness for that organism, right? The peak fitness value is at 50, right? Territories that have close to the 50th percentile for water are much more fit, result in much higher fitness payoffs than those territories that correspond to 0 or 100, that are closer to the extremes, right? Hence the inverse bell curve, representing the fitness function here. So the problem is that the critical realist strategy will have to essentially flip a coin and pick at random. You know, should it go for yellow or should it go for green? Well, it doesn't have enough information to tell, right? And half the time, therefore, it's going to be wrong, right? So imagine that it has a choice between a territory that is the 55th percentile for water and the 30th percentile. Now we can see that the one that is the 55th percentile, which appears to it as green, is more fit, right? 55, you can see if you trace up, results in a higher fitness payoff than 30, the 30th percentile. It's much lower, right? But the only information that the organism has is yellow and green. And yellow and green, from its perspective, appear to be equally good options in terms of fitness. So it's ambiguous what it should choose. Now, if it has a choice between red and yellow, well, of course, it's going to go for yellow every time. And likewise, if it has a choice between green and blue, it'll go for green every time. But when it has a choice between yellow and green, or between red and blue, it will have to mentally flip a coin, and therefore it'll get it wrong and choose the worst option in terms of fitness about half the time on average. Now, consider the strict interface strategy below. The advantage it has is that it never has this sort of ambiguity. It always knows the right decision to make, right? It always knows to go for blue if blue is available, because blue corresponds to the highest possible fitness. If it can't go for blue, it will opt for green. If it can't go for green, then yellow, and it tries to avoid red, right? There's no ambiguity given the perceptual mapping it has available to it about what the correct decision is for fitness. So in the long run, it's clear that the organism that has the strict interface perceptual strategy will generically outcompete the critical realist strategy and therefore drive it to extinction or cause it to not evolve in the first place. Now you might say, well, isn't this sort of a toy example? Why should we think that this generalizes? There are two principled reasons why this result generalizes across all possible perceptual systems at all levels of complexity. The first reason is fitness functions are mostly non-monotonic. The vast majority of fitness functions are non-monotonic, which means they, in general, are not homomorphisms of the objective physical environment, whatever the objective physical environment may be, right? The fitness function in general has a different structure from that. And so, therefore, the strict interface strategy, which is a much bigger space of possible mappings, right? Given that it's not constrained by the need to veridically represent states of the objective physical environment, it is free to give the organism a sort of fictional user interface that is nevertheless useful for guiding adaptive behavior. What this greater flexibility allows it to do is to be homomorphic not to the states of the objective physical environment, but to the fitness functions themselves, right? We can see with the water organism, blue is greater than green, is greater than yellow, is greater than red. The perceptions here are homomorphic to the fitness function, and that is what allows for it to consistently make better fitness enhancing decisions than the critical realist strategy. So the bottom line here is that the critical realist strategy gets strictly dominated by the strict interface strategy, which does not enable veridical perception but instead enables a fictional user interface. It gets strictly dominated because it is a less efficient information channel for information about fitness payoffs. An analogy here might be, consider that you're trying to send an email. Would you rather try to send that email using the fictional user interface of your desktop with the cursor and the fictional folders and all that, or would you prefer to toggle voltages directly? If you had to toggle voltages directly, as Hoffman says, no one would ever hear from you, right? Another analogy, consider you're on Who Wants to Be a Millionaire, right? And you have 4 possible answers to choose from. And let's say you have a lifeline that you can use every round, but you're playing against someone who also has a lifeline they can use every round. Now yours is the 50-50 option, right? If you get 2 of the 4 options crossed out, then you have a 50-50 chance of getting the right option, right? But if your opponent has a lifeline that only removes 1 of the 4 options, they're left with 3 left. And unless the questions are very easy, then there's going to be greater ambiguity for your opponent because there's going to be 3 instead of 2 options on the table. So in the long run, it should be clear that you will outcompete them in that context. Okay, so I know that was a lot, but I promise the hard part is over. It's downhill from here on out, if downhill means easier. And so just to show you here, this is the final results that Hoffman and his team came up with, which is that in the limit, the degree to which the strict interface strategy, which they also refer to as the fitness strategy, dominates, that magnitude increases in the limit rather than decreases as the size of the perceptual space, meaning the number of perceptions the organism can have, increases. Okay, so now a thought experiment. Imagine that we have an infallible oracle that tells us there are humanoid aliens that exist in the Andromeda galaxy. And she tells us 3 things. 1, they were the product of evolution by natural selection. 2, they are roughly as complex as we are. They have similar sized brains and number of sense organs. And number 3, they also have some form of perception. And we say, are they more or less advanced than us technologically? Do they know we're here? Is there anything else you can tell us, O Oracle, about these beings? And she says no. So we may have many questions at this point, but one thing we can ask is, given what we know about them, how likely is it that their perceptual strategy is going to be a strict interface strategy as opposed to a critical realist strategy? And the answer seems to be, well, given that the strict interface strategy generically strictly dominates, we would expect them, all else being equal, to have the strict interface strategy and therefore non-veridical perception. Of course, it's possible that the unlikelier result happens, right? In the same way that it's possible that two players playing Who Wants to Be a Millionaire against each other with the conditions I outlined earlier, it's possible that the person with the weaker lifeline nevertheless earns more points in the long run. But we, given what we know, would not expect that to be the case. We would bet the farm, right, against that happening if the timeline is sufficiently long. Okay, but now we can say, wait a minute, we're just like those aliens. We're humanoid, we are humans, right? And assuming evolution by natural selection applies in our case as well, that's how we came to develop, then we're just as likely to have that type of perception as opposed to the type of perception we've assumed ourselves to have, namely veridical perception that's enabled by the critical realist strategy. So unless we can articulate a relevant difference between this alien scenario and our own situation, it seems the same conclusion should follow. Okay, so now we're well positioned to evaluate the entire argument for the probability thesis. Number one, if a strategy A enables a more efficient communication channel for information about fitness payoffs than a strategy B, then strategy A likely strictly dominates strategy B, ceteris paribus, which just means all else being equal. Number two, the strict interface perceptual strategy enables a more efficient communication channel for information about fitness payoffs than the critical realist strategy. 3. SI likely strictly dominates CR, ceteris paribus. Number 4, if SI likely strictly dominates CR, ceteris paribus, then it is likely that the function of perception for organisms in the alien scenario is not to be veridical. That is, the function is not to grasp truths about their objective physical environment. Number 5, the function of perception for organisms in the alien scenario is likely not to be veridical, from 3 and 4. Number 6, if the function of perception for organisms in the alien scenario is likely not to be veridical, and if E, which stands for evolution by natural selection, is true, then the function of our perception is also likely not to be veridical. Number 7, the function of our perception is likely not to be veridical given E, from 5 and 6. Number 8, if the function of our perception is likely not to be veridical given E, then the probability thesis, the probability of V given E is low, is true. Conclusion, the probability thesis is true. Now remember, for a valid deductive argument like this, we can't simply reject the conclusion, which in this case is the probability thesis. If we want to reject the probability thesis, we first have to reject one or more of the premises. There are some possible objections to these premises, but we'll explore those in a future video. Okay, so we just reviewed the argument for the probability thesis, which again is the probability that the function of our perception is to be veridical, which is to grasp truths about our objective physical environment, given evolution by natural selection, is low. So now let's explore the argument for the defeater thesis, which is anyone who believes E and believes the probability of V given E is low has a defeater for her perceptual beliefs. Again, before we jump into the sub-argument directly, we're going to need some context, but this time I promise it'll be much shorter and less technical. So here's a fun little scenario to start. I stole this from philosopher Noah McKay. Temp is using what he believes to be a reliable Celsius thermometer to measure the temperature outside his home. He can read all of the numbers on the device, but the label indicating the relevant unit of measurement has been scratched off. One day his friend Barry comes to him and says, "That's not a thermometer, Temp, it's a barometer." Temp then comes to believe his device is most likely a barometer, the function of which is not to measure the temperature at all, but the pressure. Temp now doubts all of his beliefs about the temperature, which were formed on the basis of the barometer's readings. His belief that its function is most likely not to yield truths about the temperature defeats his temperature beliefs. Okay, now holding that in our memory, let's turn to scenario S2. I do not initially believe that probability of V given E is low, and instead think I am the product of a sort of evolution that makes my having veridical perception very likely. Later, however, I study philosophy and evolutionary game theory and see for myself that the probability of my perceptual faculties having the function of yielding perceptual truths about my objective physical environment, given that I am a product of evolution by natural selection, is low. Since all of my perceptual beliefs since birth were the product of these faculties, it seems that I have a defeater for all of them. Okay, so here's how the argument for the defeater thesis goes. Number 1, temperature beliefs are defeated in S1. Number 2, if temperature beliefs are defeated in S1, then one's perceptual beliefs are defeated in S2. Number 3, if one's perceptual beliefs are defeated in S2, then the defeater thesis is true. Conclusion, the defeater thesis is true. I think premise 1 and 3 are pretty self-explanatory, but the idea behind premise 2 here is that, well, the reason that Temp's beliefs get defeated is in virtue of what he learns about the function of the device. Because the function of the device isn't to measure the temperature facts, but instead to achieve something completely orthogonal to that goal, he shouldn't place any stock in his temperature beliefs that were formed as a result of his using this device, which he now knows is a barometer. Likewise, in S2, the person comes to believe that the function of their perception isn't to be veridical, isn't to grasp truths about their objective physical environment. So just like Temp can't rely on his device to uphold his temperature beliefs, the person in S2 can't rely on their perceptual faculties to uphold their beliefs about their objective physical environment. Now, one could argue that we should reject P2 because Temp's beliefs aren't necessarily defeated due to telic considerations, but for some other reason, like they're instead defeated due to explanatory or modal considerations. This is an objection worthy of response, but we'll save that for a future video where we'll explore it and many other objections. If that's something you might be interested in, consider subscribing and hitting the bell icon to enable notifications. Okay, so the hard part is over. We've gone through the long, detailed sub-arguments for the probability thesis and the defeater thesis. Now we'll briefly run through the rest of the argument, then discuss the implications. So for premise 3 here, it says, anyone who has a defeater for her perceptual beliefs also has a defeater for any empirical belief about the external world, including the theory of evolution by natural selection. So the idea here is that any empirical belief about the external world we might have is only going to be justified in virtue of our perceptions, given that we think we can trust them to inform us about the nature of that external world. But if we have a defeater for our perceptual beliefs, then it doesn't seem like we any longer have justification for those other beliefs, and therefore they are defeated as well. The defeat transfers. And premise 4 is self-explanatory because if 1 through 3 are true, then E is going to be self-defeating because the way that we came to have a defeater for E in the first place was by assuming E to be true in P1. And there you have it. Evolution by natural selection is a self-defeating theory. Now, this argument, while valid, might not be sound. There could be some way to object to one or more of the premises I'm not aware of. But to be honest, I've been workshopping this argument for months. I've talked to many philosophers about it for literally dozens of hours, and I think it works. So like I said, we'll explore some interesting possible objections in a future video. But for now, assuming it's a sound argument, what should we make of it? Well, if the physicist Sean Carroll is right in his paper, Why Boltzmann Brains Are Bad, then what's needed now is to identify some alternative theory or explanation into which the theory of evolution by natural selection can be upcycled. That is, we don't want to throw away the theory and all of the data it explains. We want to identify a deeper theory or a deeper explanation that can explain that same data at least as well as the theory of evolution by natural selection did, without putting us into the same cognitively unstable situation. What might such a theory or explanation look like? What's the best candidate here? To be honest, I'm not sure. I have a lot of questions here myself, and I hope we can explore them together. But one thing I do know is, if the argument works, we shouldn't find this discouraging. In fact, we should rejoice, because as philosophers David Albert and Raphael Liogier will explain, discoveries like this are ultimately for the good of science itself.
I don't think we could have good evidence that that the true theory of the world is one that produces this kind of cognitive instability. Okay, if it looks like our true theory of the world is producing, is putting us in a position like that, that's a bad situation. Okay, we've got to look for some other kind of theory. I think it has to be the case. I think it ought to be a requirement on an acceptable physical theory. Not just that it's empirically adequate, okay, but that it describes the kind of world in which there could be observers like us who come to have good reasons to believe that these are the laws of physics, okay? Cognitively unstable theories don't allow you to do that.
Because when it's refuted, that means that now you know what is your theory, because you have the shape of your theory, you know the limit, like the Basel, you know the shape of the field that he must cultivate. And it's very interesting. So he said, when you refute it, it's not that you